Welcome to the DotNext. So this time we are online, so only virtual handshakes, but still we're very glad that you are with us.
Same here. Hello guys, hello everyone.
Yeah, so thank you for joining us on this Saturday noon or whatever time it is in your area. So it feels like it's shiny and sunny weather over there.
No? It's gray, yeah.
Yeah, it's been better.
Yeah, it feels like you put a very powerful lamp out of the window because.
Oh yes.
Okay.
Oh yes.
So it's dark and gray here as well. So yeah, at least we're in kind of similar conditions on this Saturday. So I think you are going again to give us a great set of different kind of demos and practical hands-on things of how to do different performance things, right?
Yes, exactly. Yeah, the goal is really to give you some tips and tricks and some source code to write your own tool to monitor how the .NET application is working.
Yeah,
that's the goal.
Yeah, that's what we like your talks for. So let's then just start.
Okay, thank you very much, Igor. So hello everyone. Welcome to this .NET memory and CPU profiling in C#. The presentation, as I just said, will be about sharing with you how to write your own tool in C# and to monitor memory allocations, knowing what types are allocated, how many times, for what size. Also get the call stack that leads to these allocations. I will also focus on CPU sampling, how to get every milliseconds the call stack of each and every thread in an application, showing you how to do either a live recording or a file trace recording. And I will also discuss the how to merge the call stack in order to get some meaningful information. And I will mostly focus on the Windows side of the story. For the Linux side of the story, Kevin will continue, and he will tell us the nice way the nice things you can do on Linux. As I said, this is a C# session. If you're interested in implementing your own native profiler, please watch Pavel's session from last year. You will get everything you need to do that. So if we are not writing a native profiler, how will we get the information that we need? Well, when a .NET application runs, it's possible to ask some providers inside the application to send messages that are called events. So you can have a kernel provider, you can have a .NET provider, and the events that are sent, for example, for the .NET providers are documented. And here is the documentation that you will get. And you can see that you have a bunch of different kind of events. You have exception-related event, contention event, and I will focus today on the garbage collection event. These events are called keywords for a provider. And so the goal of the tool that we will be writing is to enable the right provider, select the right keyword to get the right messages, the right events. And then once you've done that, you will be able to, at runtime, record and read the event, analyze them, or get them into a file. On Windows, you will rely either on ETW, for event tracing for Windows, or the event pipe pipeline. On Linux, it would be LTTNG or event pipe. I have already covered the event pipe scenario last year, so please feel free to watch the last year session about event pipe. Today, it will be based on ETW. An ETW session is the thing that you will need to create to get all these messages, and you need to understand that when you create an ETW session, you get the messages for all the processes. I will come back to this fact and how it impacts what you will be doing. So how in C# you are able to create an ETW session and listen to these events? Well, you can use the trace event NuGet package that is provided by Microsoft, and you also get access to the source code because it's in the Purview repo. the performance tool that is provided by Microsoft, and you can get access to the source code. So what you need to do is to create a trace event source that will wrap the ETW session, and then you will listen to this event through normal C# event. So you will attach your event handlers to one of the two properties. One is the CLR. It's a trace event parser that provides this event that you will listen to from the CLR, and also the kernel trace event parser. So it's quite simple. I want to show you some code because slides are nice, but I often prefer to dig into the code. So this is the source code of one of the examples in that solution. This is a solution that contains a few profiler, some about memory and some about CPU. All these source code is available on the Git repo. The link to my Git repo is available in the slide, so you will have access to all that source code. So all my profilers are built the same way. First, you need to create a trace event session to create the ETW session, and you give it a name. Why is it important to select a meaningful and kind of unique name? Is because when you will be doing some debugging with Visual Studio of your tool, you might stop a debugging session and without closing the ETW session underneath. And so there will be an orphan kind of ghost session, and Windows is allowing only a limited number of ETW sessions to be created. So if you do that over and over, you won't be able to create a new one, and you will have to reboot your machine. But there is a better way than rebooting your machine. You can use the logman command, the logman-ets command. If you type that command, then you will get the list of all the sessions that has been created, and you can just stop one session by giving it a name. So that way you will clean up your ghost session, and you will be able to continue to debug your tools.
Christophe.
So once the session is created, yeah.
One
Got
thing.
a question?
Can you? Yes, not a question, but a small note. Can you make your font in Visual Studio a little bit more zoomed in, so a little bit larger, so that we can?
Is it good?
Yes, I think yes. That looks better, much better. Thank you.
Okay.
Sorry for interruption.
No. Please interrupt.
You can make it a little bit bigger. You can make it a little bit bigger.
Okay, this one?
Yeah, perfect.
Okay. So once you've created the session, you do your stuff, and I will go back to that through some boilerplate code that is provided by the profiler that I have written, and then you dispose the session when you're done. So let's look at what kind of code you have to write. It's in the start async function. And the start async function, what it does, it will set up the provider. Remember, we would be interested in getting even from the CLR provider or the kernel provider. And then I will wrap the session with an event source from trace event. And then I will set up my event listener to receive the event, and I'm calling process. That function from the source is a blocking call. What it means that this function will not return until the until the session is disposed. So that's why I'm wrapping all that code into a task, because since I'm the main thread of the application, to call the dispose, I have to listen into another thread. Hence the need for that for that task. So remember, I need to enable the provider. The code to enable the provider is using a few functions from the session. The first one that you need to call first is enable kernel providers, and you pass some of the keyword. I will go back to which keyword to use for what, but now I just want to show you the function you need to call on the session. And if you want to enable another kind of provider, you call the enable provider function with the GUID, and trace event is providing a few GUIDs, and then you pass the list of the keywords, meaning the group of events you are interested in, and with what kind of verbosity to get this event. Once this is done, you register your callback that will process the payload of the events you are interested in. So it's quite simple, and it's always the same thing. You create the trace event session, you dispose it when you're done, and you enable the provider you want, and you listen to the event in your event handler. That's it. So it's pretty straightforward. It's always the same thing to do. So now the rest of this presentation will be to describe what kind of event are providing the information we want. And I will start with the memory profiling case. So here you have the choice between two events. You can either use the allocation tick event or the GC sample object allocation event. Both have pros and cons, and I will show you the detail for each scenario. The easiest one is the allocation tick event. This event is sent by the garbage collector after the application has allocated 100 kilobytes of memory. And what you get with the payload is the name of the type of the instance that was last allocated to reach that 100 kilobyte threshold. And also you will get what kind of allocation it was. What I mean by that is the allocation greater or equal to 85,000 bytes that would end up into the large object heap? In that case, you would get a large allocation kind, and otherwise it will end up into the Gen 0, and it will be a small allocation kind. Last but not least, you get this property, which is the allocation amount 64. And unfortunately, this is not the size of the last allocation. It's the cumulative size of all the allocation that reaches that 100 kilobyte threshold since the last event. So to sum up, you get real sampling of the allocation. You get the name of the type, if it's an allocation that end up into the large object heap or not, but you don't get the information about the size of the allocation. So let's run the sample application. So I will start with the allocation tick profiler, and I will need to use a sample application, and I have prepared for you a simple WPF application. Is it visible on the screen? Igor, is it big enough? So you have the process ID here, yep. 25024. So we'll just set up 25024, 25024, and I will start the application. So I will be allocating with my tiny WPF application some arrays of bytes. So I'm looking for my, yes, here it is. So it will be too small for you. Let's make it bigger. Is it bigger?
It is.
It should be, it is,
yeah,
okay.
Yeah, maybe if you can make it a little bit, the font I mean.
Okay, something like this.
And one more step.
Okay.
Yeah, perfect.
Okay. So here I will allocate, for example, 3 arrays in the large object heap. And what I'm expecting is that I'm getting some event over there with either it's a large or a small and the name of the type. So this is exactly what I get. If I want to allocate like 2 that will be smaller than the 85,000 bytes threshold, I will get 1 event because it will be 84 plus 84, more than 100 kilobytes. So I will get 1 event, and I will know the name of the type. So this is really what I want. What is missing is the size of each allocation. So I have kind of partial sampling here. So now that I have got this, what I have to do is simply enable the CLR provider and the keyword, which is GC. If you do that, you will receive the allocation tick event. And so this is what you need to do when you enable the provider. The next step is how to get the call stack that leads to this allocation. Well, what I want to get is something like this. So I will change the code to dump the call stack each time I get an event. So I'm running the same application. I hope it will be big enough by default, but I'm pretty sure it won't. So something like this. Make it big, and I will allocate again. And this time, in addition to the name of the type, I will get the call stack. So I will get the list of all the method. This is the name of my own allocate method that does the allocation. That's all the WinForm or WPF, code that end up through the click of the button. And I can see the name of the function in the CLR. That's even this one is the one that is called to fire the GC allocation tick event. So you get a full description of all the method that leads to this allocation. So how would you do that? How would you achieve that? Well, it's quite simple. You just wrap the session with that specific type, the trace log event source. Once you've done that, you have almost nothing else to do. You don't have to listen to specific events. That source will proxy all the events that it needs to compute the call stack, plus transform the address on this call stack into either native function or managed function. So what you have to do, you have to set up the keywords corresponding to these specific events. Even if you don't have to listen explicitly to the event, you have to tell the provider to emit this event. I will show you later on how to do it yourself, meaning what kind of event you should listen to do it manually. But let's first start with these different providers. For the kernel provider, you have to mention that you need the message each time a DLL is loaded into a process, because that way the magical class will be able to load the corresponding symbols to do the mappings between the address on the stack and the name of the function. For the CLR provider, what it needs to get the just-in-time compiler messages, again, to be able to build the mapping between an address of a JIT function and its name. And also the specific stack keyword that tell the CLR to send some specific event. I will go back to that later on. And last but not least, I'm asking the what is called the CLR rundown event parser, the provider. This one is almost the same as the CLR provider. The main difference is that it's recording all the events, and when it's enabled, it will send all these events. Why is it important? Because if you start an application and it runs, the method gets just-in-time compiled, and then you start your profiling session after all that processing. You won't get from the usual CLR providers the events. You need to ask the CLR rundown provider to send all the events that has been recorded. That's why you need that provider. Okay, so how do you get the call stack? Well, it's really simple. You just have to call stack from the payload of each event, and that's it. With that call stack, you get a trace call structure. That data structure is a linked list of all the frames. And the frame 0 is the last frame on the stack. It is the top of the stack. So you enumerate all the frames, and you chain frame by just getting the caller property. What you have to do is for each frame, you need to check that the method is available. If it's not available, it means that the magical class didn't do its job, and you need to look up the symbols for that specific module that was where the method was from. And once this is done, you can just call the full method name property from the code address corresponding to that frame, and you get the nice, good-looking name of the function, either a native function or a managed function. Well, now you know how to do that. The easy way, it's time to go more complicated way. First, because it would be good if we could go beyond the limitation of the memory sampling of the allocation tick, which is that you get the name, but you don't get the size. So I'm interested in showing you how to get the size and much more accurate numbers about the allocation. What I'm interested in getting some events that will tell me which class has some instances that have been created, how many of them, and for what size. And this is exactly what the GC sample object allocation object is. You have two kinds of keywords for that. You have the high and the low keywords, and the main difference is how many events per second you will receive. For the low is at most 5 per second, and for the high is at most 100. It really depends on how your application is allocating, but usually you could start with the low. So when will you get this event? You will get this event after object has been allocated, and each event will contain an ID of the type. Why is it an ID and not a name? Because for performance sake, the CLR is using internally some ID to identify the name, the types when they are doing some allocations. And it would be expensive to each time there is an allocation to get the name of the type. So they just, in the payload, give you the type ID. And you might ask the CLR to give you the mapping as a bulk of all the types and their ID. That's why you need to process the type bulk event type that will send you an array of ID name. And you just have to build a dictionary between the two, and that's it. So in that specific GC sample allocation, object allocation, in addition to the type, you will get two numbers. One is the object count for type sample. It means that you will get the number of instances that have been allocated since the last event. Maybe if you have 6 allocations, you will get 6 here. And in the total size for type sample, you will get the sum of the size of these 6 allocated objects. This is exactly what we want. We want to get the exact number. It will be sampled over time, but we will have everything we need. So this is great. The main limitation is the fact that in order to get this kind of information, you have to tell the GC to keep track of the allocation for each type. So you need to tell the runtime before the process starts. So you need to start your profiling tool before the real process is starting. And that could be a limitation, for example, if the application is a Windows service. In that case, the Windows service might even be started before you just log in on the machine. So that's the main limitation. And beyond that, it's really nice. So how would you do that? Define the keywords that are needed, either the low or the high. Notice that if you ask for the 2 keywords for that provider, you will get an event per allocation. Never do that, okay? Because that would push a lot of pressure on the CLR. What I mean by pushing a lot of pressure is that you will ask the CLR, the GC, to create such event on each allocation, which is very often in a .NET application. And it will send that through the ETW event pipe, either the ETW or the event pipe, and that will have an impact on the performance of your application. So start with the low. If you need more than that, pick the high, but don't pick both. And in addition to that, you need to add these 2 keywords, the GC heap and type names, and the type keyword. Why? Because once you've done that, you will receive the type bulk type event, and in the payload, you will get an array of type ID and type name. This is how you could build a dictionary. Here, the name of my dictionary is in the process type mapping, but that's just an implementation detail. Just build a dictionary, and that way, when you will receive the GC sample object allocation event, you will be able to know the name of the type. Now that we've done that, how can we get the call stack for all these events, and how we will be able to change the address that we get from the call stack and transform them into a name of a function? We have 2 cases. The first one is the manage case. In case of a C# application that gets compiled into an executable, there is the compiler, the C# compiler, will generate some intermediate language code. And when the application starts, the just-in-time compiler will take that IL code and compute some assembly language corresponding to the IL code. That's how .NET works. And when the just-in-time compiler is doing that, it will send some event. These two events, the method load verbose and the method DC start verbose v2 events, are sent. And what you will get is the name of the method. You will get the name of the type and its namespace, plus the signature. So that's nice. You get one side of the problem. You get the name of the function. But how will we be able to map an address on the stack to that specific method? Well, we get two additional information. We get the start in memory. So you will get that information where in memory the binary code starts for that function. And we also get the size of the function. So what it means is if you get an address on the stack, and this address is between these two numbers, the start and the end, so you know that you are in this function. So again, that's just a question of mapping. I'm computing a list of all the JIT method, and when I need to figure out the name of the function, I'm just passing all this list, and when I find a match, I put this into a cache, and so the next time when I get the same address, I'm able to find the same function name. That's the most complicated part, in fact, of the code. The second scenario is it's not a manage method, but it's a native function, like the one that we've seen with the CLR. Well, in that case, the C# compiler this time is generating directly the assembly code that is mapped into memory. But I don't want to deal with that, okay? It's just something that it's overcomplicated. And I'm quite lucky because I could use the DBG HLP Windows API to do that for me, to do all the mapping for me. So what I have to do is set up and initialize the DB HLP API with the seam set options and the seam initialize, And then each time a DLL, a module, is loaded in the process I'm interested in, I'm calling the seam load module 64 function, and that will do the magic to load the corresponding PDBs, the corresponding symbols that contain the mapping between the address and the name of the function. Something close to what I've explained to you for the managed scenario. And then when I need to do the translation between an address and to get the name, I'm just calling the seam from address function. For the JIT method, I already explained what you have to do. And the last part of the magic is how do I get the call stack? When I'm adding the stack keyword to the CLR provider, what I'm telling him is instead of sending the usual events, I want to send pairs. So each time there is an event that is sent, like the allocation tick, the same thread immediately after sending the event, it will send the stack walk event. And that stack walk event will contain the call stack that reach that code. So what you have to do, you have to keep track on a pair thread basis, and it's easy because each event contains the process ID and the thread ID that emitted that event, and you keep track of the last allocation event. And when you receive the stack walk, you get the ID of the thread that sent the stack walk event, and you just do the mapping between the two, and you can attach that call stack to the allocation and do some computation on the different call stack. So what you have to do when you get the call stack, this time it's not a linked list like it was before. It's what you get is the number of frames. So it's in the frame count, and you just iterate on the array of that, and you call instruction pointer and which frame you want at which position. You use just that function. It will give you the address of that specific frame, and that's what you need to do. I'm done with the memory part, and it's basically the most complicated part because I've explained what you need to do to set up the session, how to enable the providers, what are the keywords, how to attach your message handler. And for the CPU profiling, it's much more easy. Why? Because you just have to use one provider, which is the kernel provider. You will have to set the profile keyword, and you are not even interested in getting what inside the payload because the call stack will be rebuilt for you by the magical class. So what you have to do, you have to enable the kernel providers, as always, and this time you add the profile keyword, plus you are telling him that he needs to capture the call stack for all the events that will be sent. Once this is done, you have the same stuff that I've already showed you. You create your the task. In the task, you are wrapping the session with the source, the magical type, and you are just listening to one simple event here. I didn't take the time to have like my specific event handler. I'm listening directly onto the perf info sample event from the kernel trace event parser, and I'm getting the call stack for that event, and I'm merging the call stack. I will go back to the merging later on, and I'm calling the process blocking call that I've already explained for the memory, and that's it. It's really, really simple. So let's see what we can do. I will take my CPU sampling profiler example, and I will run, if I'm able to start it as sample project. I will be using another tiny application called a simulator, make it a little bit bigger. That allows me to do some repeated actions that will be recorded by the profiler. So I'm starting the profiler, make it bigger. Wow. Okay, so that's nice. This is the kind of thing that you don't want to see in a demo. So let's remove that problem. I will stop. Yeah, I got a crash somewhere, and since I have WinDBG attached as a default handler, I can't have two debugger on the same process. So I hope I didn't kill everything. So I will close that, and I will try again. I hope that I won't. Okay, so I think I have a big problem with my environment right now. So I won't try to...
so we call that the Christophe effect.
Yeah, that's the Christophe effect. And it's not a joke. It's something that we've seen when we are working together with Kevin. Everything was perfectly fine. And then you don't know why. When I'm trying to do something, it's just simply breaks. So I will close... I will close everything, and I will try to start again to see if it's a little bit better. So I will start my Visual Studio again, and okay, so I can't even open Visual Studio. Wow, that's a nice effect. Let's try again. Small, gentle, please. Okay, and I will start Visual Studio. It's so slow. Run as administrator. You need to start your debugging session as an administrator when you are doing your debugging, and start the project, the profiler project, but you don't need to do that when you will be running your tool, because you have two different ways to do that. You can just either select the user that will run the tiny tool as a member of a specific group, or you will have to enable a certain privilege, and I will show you which privilege you will have to add. So I'm waiting for Visual Studio to start. It's so slow. And when this is done, maybe I can just go back to the slides, and while it's loading, I want to show you those. That's exactly what I've just explained. You need to just make that user part of the performance log user group, or you just add to grant this trace log access real-time permission. And once you've done that, the profiling will be able to run. If you don't do that, you will have an access denied, which is not the error we got here. So it's not that specific problem. So let's go to the CPU sampling profiler, and I will have to start my tiny application again, but I'm pretty sure I just closed it. So I will need to start it there. Sorry for the problem, guys. All the source code is available for you. I don't know why it's so slow. Maybe it's because I'm sharing the screen, and so we'll start the simulator application. I will make it a little bit bigger, something like this. I need to set up with that specific process ID because I want to get only that information with my CPU sampling profiler. My Visual Studio is just extremely slow, but I should be able to reach that specific screen to set up the process ID I want. And once this is done, crossing fingers, please, guys, cross your fingers. Kevin, can you do some specific dance that might help me? And if it's not working well,
I can, yeah.
Yeah. Let's wait for the compilation to end. Here it's still compiling. And what the tool is doing is listening to these events. Okay, so it didn't take my decision to change the startup project. Let's start again. Okay, no error. So this time it seems to work. And I will start allocating a bunch of memory in loop. This is what this tool is doing. On that part of the screen, this one will collect all the CPU samples, but this time I'm not doing it live. I'm asking ETW to generate a trace file for me. And while it's doing this, it's just limited access to the CPU, just storing on disk. And so that way I'm not impacting how the application is working. So now what I will be doing, I will stop my profiling. That big screen, I will make it a little bit smaller because you will see that it will collect all the call stacks and we will start to get the symbols for the stacks and build all the call stack. And this is kind of summarizing all the call stack, doing some computation, merging the call stacks. And from that call stack, from the merge call stack, what the program is doing, it's kind of rebuild the parallel stack that you have in Visual Studio. The parallel stack it computes all the kind of root frames that all the threads have, and then fork to the different execution paths. And from all these different execution paths, it builds a kind of tree. And so you will be able to see that tree, plus for each part of the tree, how many times that specific frame was found on any call stack. And this is what is done here. It's just computing. It can take some time because the symbols might needed to be downloaded from the internet. And once this is done, the tree itself is computed, and I'm waiting for the tree to appear. It will be a set of blue lines. So I'm waiting for the blue lines here. It should be quick now. Let's make it smaller so the scrolling will be faster. That's a trick for you guys. If you want to make your application run faster, just reduce the UI and you will get everything. So that's the information corresponding to the merge call stack. You can see a kind of tree and you have the numbers in front of each and every frame. I want to go to the top. I know that Kevin prefer tree in the other way around, meaning starting from the bottom, but here I prefer to have the this view. And what you see here is the path of execution that leads to the most common frame. So I've lost my blue lines. Okay, here are my blue lines. And you can see here that I got 2,422 times that call stack. And I can go down and go down and go down to my tiny run function from my random allocation class. And you can see, you can find the same method that we've seen with the WPF example up to the fire GC allocation tick v3. And for each one, you get the number of time it's been executed. So here, you can do that kind of live. And this is what is interesting. But what is also interesting is being able to do that in a post-mortem way. So to do that, you need to create a file, and this is what I've done with this example. And if you do that, the file that you will get, you will be able to open it with Purview. And how would you do that? What is the code change compared to what I've shown you earlier? Well, you still have to create your trace event session, but this time, in addition to the name, you pass a file name, and that's it. You enable the provider you want. In that specific case, it was only the kernel provider. And once you've done that, ETW will automatically serialize all the events for you in that file. So once you dispose the session, you are able to work on the file. And how would you do that? You will get a tracelog class, a tracelog instance of the tracelog file. I'm starting to be tired. So you use this tracelog open or convert method to get a tracelog instance. That tracelog instance mapped to a .etlx file that will be generated for you from the initial trace file. It will contain more information such as the symbols that will be able to be used by Purview. And next, you will pass all the events from that file. This time, there is no strongly typed event handler. You have to deal with each and every event. So you filter out the events that are not for the process that you are interested in, and you need to know what are the ID of the events you want to look at. And here I have got the opcode and the task queued, which maps to the keywords that we have defined. Everything is extracted from that sample of Purview. So there is no reverse engineering. No reverse engineering here. It's just looking at the kind of source code documentation. And once you've done that, you know that this is an event that you are interested in. This event will contain the call stack you want to merge. And once you've done that, you just merge the call stack and do the computation. Okay, so I think I'm done. How many times do we have? Am I late compared to what we've planned, or I have like 2 minutes left? Kevin, do you give me 2 more minutes or
not? 1:30.
1:30. Okay. So once you've created the etlx file, you can just open Purview and look at inside this etlx file. You open Purview, you just open the etlx file, and you get.
No, Christophe, we're not seeing your screen anymore. There we go.
Really?
Yeah, now we.
Okay, sorry guys. So I was there and I was looking at the etlx file, and I was opening Purview to load the etlx file. You just double click in Purview, and you get here a set of views, and in the views you have the CPU stacks. And so in the CPU stacks, you select the process, because remember, with ETW, you get the events for all processes that are running during the session. I'm interested only in the simulator one. And in the simulator, I can get the call stack loaded, and I can do some advanced analysis with Purview. And this is something that is really, really powerful. I don't want to do a demo of Purview here, just to show you that you can just look at the thread and the call tree in Purview and get a more advanced UI. That's the one that I've shown you in my tiny demo. And you get some numbers like inclusive numbers, exclusive numbers, and you find the same kind of call stack, but in a more powerful way. You can filter, you can group. And this is something that is good to generate these trace files for the reason that you won't consume too much CPU while you are recording them, and you will be able to do a post-mortem analysis for that. Thank you for your time, Kevin. So now it's your turn, and I'm sorry that I had to deal with my Christophe effect during the demo.
Can you unshare your screen?
Yes, I will try to unshare my screen. Again, I need to find the control to unshare the screen, and I'm stop sharing.
All right, so I will be taking over here and preparing my slides that are here, and we should be good. Yeah, all right. So I think we've seen enough cats in Christophe's part, so I will be taking over and putting in some red pandas instead. I will be talking about pretty much the same thing as Christophe, except that this time is going to be on Linux. So why having a part dedicated to Linux? Because you may remember this slide from Christophe's part, and on Linux you don't have ETW, and you don't have the kernel logger. And so that's how you may feel at first if you want to do some profiling. But fear not, because there are alternatives. For all the .NET events, such as allocation ticks that are needed to write a memory profiler, you can get them through event pipes, and it works just as well as ETW. But for the native profiling, since you don't have the kernel logger, instead we will use perf, which is a go-to tool for profiling on Linux. So if you never use perf, just a quick reminder of the commands. You can use perftop, which show you a live view of what is using CPU on your system, which is pretty nice to do an early investigation. But most of the time, you will want to use perf record, which run a profiling session like a traditional profiler and save everything to a file. That's a typical perf record command line. -F is a sampling frequency. So here we're asking perf to sample the CPU 999 times per second, so almost once every millisecond. So why don't we put 1000? Because most likely in your application, you have stuff occurring like every 10 milliseconds or every 100 milliseconds. And so if perf sample the CPU every millisecond, it will tend to synchronize with your application, and this will skew the data. So by putting 999, we slightly desynchronize perf, and you get better results. -P is a PID. -G tells perf to record the call stacks, otherwise it just records the top frame. And sleep 10 is to sleep for 10 seconds. And you can substitute sleep 10 with any command, and perf will run as long as this command is running. One more thing, you need to define an environment variable if you want to have the manage symbol, and I'm going to demonstrate that to you right now. So yeah, it should be big enough. So I have just a dumb console application that is going to run in background and eat some CPU. Here is a PID. And if I run perftop, I have a live view of what the application is doing. And you can see that some symbols are resolved, and some other we just have addresses. And that's because in a managed application, managed functions are compiled at runtime and not at compilation time. And so their destination address is not known when the PDB file is created. So they are not mentioned in the symbol, and so perf cannot resolve them. So Christophe didn't have the problem because ETW send an event every time a method is JITted with this address, and he used that to resolve the symbols. On Linux, we don't have ETW. So instead, what we do is, so first I'm going to kill the application, and you define the com+ perfmap enabled environment variable. And if you do so, and you start your application again, this time, if I look into the temp folder, I will find a perfmap file with my PID. And what happens is every time the JIT is going to compile a method, it's going to update this file with the address of the method. And then perf knows how to find this file and use it to map the symbols. And so if I return to perftop, this time we see that all the symbols are resolved, and I can see what is using CPU on my machine. Okay, so it's all nice, but this is a session about tooling. So what kind of tools can we write for perf? I can think of two kinds of tools. Either we can control perf, start and stop the session, or we can listen to the results of perf and, for instance, display things in the UI. And we are going to see both of them. So first for the controller part. This is actually a real use case that I had back when I was working at Criteo. We had an application that was suffering from abnormal GC pauses. Like once or twice every hour, we would have a GC pause that lasts 100 milliseconds instead of 10. And I was trying to figure out why. And for that, I needed to profile the application. But this was a 32-core server with a lot of traffic. And so I could not just run a perf session for 1 hour because the file would have been 50 or 100 gigabytes and it would have been very hard to use. I needed a way to capture a perf session just around a suspicious GC, but I could not predict when they would happen. So what I did is I wrote a small tool that listened to the GC events from the application through the event pipes, and it recorded them. At the same time, my listener started perf, which captures stack traces from my application. And I run a short session of perf, just 5-minute sessions. After the 5 minutes, perf would generate a file and exit. And then the listener would look at all the GCs it had recorded and look if there was any suspicious GC. And if not, then it would take the file, delete it, and start a new session of perf for 5 minutes. 5 minutes later, we would have a new file. The listener will look into it. And this time, if we recorded an interesting GC through the event pipe, the listener would move the perf file to a backup folder and keep listening. And this way, I could let the tool run for a whole day, and I would just have a few small perf data files that I could analyze, each with one GC of interest. So I won't get into the technical detail of this listener. To control perf, it's just a matter of launching the process and stopping it, so not very technical. And to listen to event pipes, as Christophe mentioned, he already covered that last year, and so there are plenty of resources available. So I will skip this. But let's spend more time on the listener side. So basically, what if we want to listen to the output of perf and do stuff with it? So the recommended way is not to directly parse the binary file from perf, but instead to run perf script on it, which will convert it to text, which is much easier to process. And you may already know this flame graph project that takes the perf output and converts it to a flame graph. So personally, I don't really like this representation. I've never been able to do anything with it. But what I like in this project is the stack collapse perf script that you can reuse for your own purpose. What it does is it takes the output of perf script and removes the time axis to aggregate the stack traces, which makes it much easier to process. So to give an example of what it does, this is a typical output of perf script. Basically, every time perf samples the CPU, you will have some information and then the stack trace. Then 1 millisecond later, you have some information, the stack trace. Then 1 millisecond, and so on. And your UI, most likely all you want to know is what percentage of the CPU each method has used. So you don't really want the time information. And what stack collapse does is it takes that file and it just counts each stack frame and display user results. So all we know here is that the stack trace method 1, method 2 was seen once, and method 1, method 3 was seen twice, which is much easier to process than the file we had originally. Here, it's literally just a matter of executing string.split, and that's it. And as an example, taking this collapse file, it took me less than an hour to drop that into a WPS tree view and have my data visible as a tree, which personally I prefer to the flame graph, but it's really a matter of personal preference. So that's how to load the perf file. But what if you want to process the perf events live? For that, on Linux, most things work with pipes. So basically, we would launch perf record, and add a pipe and then my own application, and we would get the events from the console input stream. To get those events, you need to understand the binary format of perf. So how does it work? First, you have one magic number that helps you confirm that you are indeed talking to perf. And then you have a stream of records. Every record has the same header. It has a type. It has some information we're not going to use. It has the size of the record, and then some content that depends on the type of record. We are going to be interested in 3 types of record. First, the attribute record, which contain, at first glance, very interesting information, such as the instruction pointer, the ID of the CPU the code is running on, the full code stack, so everything we need. But if you look at the values, they don't make any sense, and we're going to see why. Then we have the mmap event, which is called raised once for every library loaded in the target process. And it contains information such as the name of the file and the address in memory in which it's loaded. And we're going to need it too. And then every millisecond, or depending on what sample frequency you used, you're going to get a sample record. And it's just binary data. But if you remember our attribute record, it's actually offsets into that file. So basically the attribute record tells us where in the sample record we will find information. And the reason it works like that is because depending on the version of your Linux kernel, or depending of the flag you give to perf, you won't get the same information. And that's why perf is using a dynamic format. And the attribute record is telling you what format it's using for this session. All right, so you already have enough with those events to capture the address of the method in the target process, but that's not very useful. How do we translate this to method names? For that, we need to understand how symbols work. So imagine you are compiling a library. The compiler will put your method into some places into the library. So for instance, we will have a procedure at 13ff and a procedure at B810. The symbol file is just an index that is going to tell you, okay, at 13ff, this procedure is named method 1, and at B810, this one is named method 2. But this is not enough to convert our memory address to method names. Why? Because when your code is running inside of an application, inside of its memory space, your library won't be loaded at address 0. If only because, in theory, only one library could be loaded at address 0. So it will be loaded, for instance, in address 1000. And so it means that method 1, which was at address 13ff, ends up at 13ff plus 1000, and so that 23ff. And same thing for method 2. So it means that to translate your memory address to method names, you need the symbol file, but you also need the base address of the library, that is the address in memory at which it's loaded. Okay, so to put everything together, how do we get all that information? First, we have the mmap record, which is going to tell us that libcore CLR is loaded at address 1000. When we receive this event, we're going to find the symbols for core CLR and create an in-memory table when we are going to say that at 23ff of the target process, we will find method 1, and so on. And then we will get a stream of sample record, which contains a code chain, which are just memory address. And for each memory address, we're going to look into our in-memory table and find the method that starts just before. Because we are getting instruction pointers, and it's very unlikely that the instruction pointer is going to be at the very start of the method. So we need to look back a bit and find what method starts just before it. So for instance, we have CA21, and we look into the symbol table, and we see that CA10 starts just before. So this is the method. And by applying this, we can translate those addresses to symbols. All right. We need one last thing. We need to understand how to get the symbols. So we will get them from two sources. For the manage symbol, I mentioned the perf map file earlier. And if you look at it, the perf map file is actually just text, and it's just mapping a memory address to a method name. So this is going to be really easy for us to parse. Also note that this is, since this was generated at runtime, this is the actual address into the target process, so we don't need to do any kind of translation like I explained. But then for native symbols, on Linux, on native library on Linux, the symbols are often embedded directly into the binary file, or if not, they are available separately in a .dbg file, which is a Linux equivalent of .pdb. And so I already downloaded the symbols for the core CLR assemblies. You can download them using the .NET symbol tool. And then I can use the nm command, which is provided with Linux, to parse this file for me. And so if I run it, I get a bit like the perf map, I get a table which gives me the address of the method inside of the file. So I need to translate this one, and the name of the symbol. And so now I have everything needed to build my application. So just really fast, let's zoom in a bit. This is an application that opens the standard input in which perf is going to push the value. We check the magic number, and then we have an infinite loop in which we're going to read the record sent by perf. And when I have a mmap record, I'm going to read the symbols, either using the perf map file, so I'm literally just reading the file and parsing it as text, or using the nm command, so I'm running nm and parsing the output. And then when I get a sample event, I'm just going to get the address of the method, and then I will look into my symbol table and try to convert it to a method name. And so if we put everything together, I don't remember what was the PID of my process. It was that. So now I should be able to run perf record -p my process. We'll say 99 for the frequency, -g, and I'm adding no buffering to tell perf to send me the events as soon as they occur. Otherwise, it will buffer them for a few seconds. And I'm going to send that to my own application, the one I show you. And if there is no Christophe effect, here we have our own version of perftop, and we see live what is eating CPU into the target process. All right, and I think that wraps up. So where is my slide? There we go. So in conclusion, Christophe and myself have shown you how to build your own tools on top of profilers. The idea that writing a native profiler is very hard, but most of the time, somebody has already done the work for you, and they provide a way to use their work in your own way. So basically, if a profiler isn't doing what you want, it's often, I wouldn't say easy, but it's often possible without too much effort to write your own tool on top of it and get exactly what you need. So we've provided a few links to my blog, to Christophe's blog. Also, the source code for our presentation is available. And I think that's about it. Do you want to add something, Christophe?
No, there was no Christophe effect during your demos, but beyond that, no, nothing.
Excellent, thank you. That was a pretty packed demo session, so we've learned a lot of different kind of things. And I think I have the first question now to Kevin. So I was looking at what you were doing with all this Linux tooling and mapping things here and there and back to the addresses and everything. And I have a kind of a feeling that it looks pretty similar, or not that different from what we had like maybe 2 years ago, or when .NET initially came to the Linux platform. So what is your view and vision how the Linux tooling is evolving, and will we get something as like built-in and streamlined as we have on Windows?
Well, the tooling is making a lot of progress. And in fact, Christophe and myself didn't mention it, but there is already a profiler bundled in .NET that you can listen to event pipes. Though personally, I don't use it because it has a very large overhead, much more than the native profiler. But yeah, whether that's on Windows or on Linux, the native profiler is actually not part of the .NET ecosystem. That's something that can profile everything, and that we're using for .NET. That said, or to listen to perf for a .NET application, you can also use the purview script that is provided by the .NET team. And it does all the stuff of setting up perf, capturing the events, and then storing it into a file that you can open with purview. So for a simple investigation, it's likely more than enough, and you don't have to do all that crazy matching of symbols and so on.
Okay, thank you. And then the next question is about the overhead you mentioned. So as far as I understand, we've been told that ETEW has a very low overhead, so you can, unless you enable this high keyword where you get these, or both of them, which will be very bad, I think, for performance. So does it mean that both the Linux version and the Windows version of what you've shown can be safely run on production with, well, some precautions?
Yeah, I would say so, yeah. And the impact is not really due to the transport itself. You mentioned ETW, but it's also due to the fact that the CLR itself has to construct the payload of each event, and that could be expensive. So that is something that you need to take into account. That's why when you are building your tool, you should try to focus on the events you are interested in. For example, we have a tool called Metrics Collector that listen to these events to build some metrics about exceptions, contention, GC information. And we've realized that on some specific, very large application, we might want to only listen to the GC information, for example, because the exception events would have an impact on the performance of the application. But remember, I'm talking only on very specific application that are handling thousands of requests per second, and it's a very, very high-end scenario. So to answer your question, you should measure what is the impact of your tooling, but from what we've shown you, you shouldn't have that much impact, no.
Okay, thank you. Let me quickly check the chat. Okay. The next question is what you were showing was all happening on your computers directly, but in the modern world, well, where everybody goes to containers and everything, or clouds and running things in cloud native Azure functions, AWS Lambdas. So what is the approach? How far can we apply this approach when we're talking about containers and the other things?
Kevin, do you want to start?
I'm not sure. I
can start. Yeah, I can start. It's up to you.
Go on.
I can give you what we are doing in Criteo. So in Criteo, we are using Mesos and Marathon as a container environment, and each application is running in its own container. So what we are doing, we are adding what we call sidecar application that are started in the same container as the application. And the sidecar application is listening to the event pipes, for example, to get the event and build the metrics. But we also have what we call a profiling agent that runs as a sidecar and that we can access through a HTTP endpoint. So security is very, very important, and you should protect this endpoint. And this is also the way that Microsoft is going with the preview of a tool called .NET Monitor, the .NET Monitor tool is a sidecar application that runs aside your normal application, and you can access to that .NET Monitor through an HTTP endpoint, and you can trigger the creation of a memory dump. You can get the GC dump created for you, and you can get the counters. And I'm pretty sure that they will expand the kind of information that you can get from that sidecar. So to answer your question, the current way of doing things that I'm seeing both internally and at Microsoft is to add features inside the sidecar and access the sidecar through a protected HTTP endpoint.
Also, another thing to mention is that if you target only one PID, if you're not trying to profile the whole system, then you can run perf in user mode, so you don't need special permission. So it's a good candidate for running in the container alongside your application.
Okay, thank you. And another thing is that you mentioned that Event Pipes has some overhead, but on the other hand, Event Pipes is kind of a cross-platform thing. So any chance that Microsoft will invest something and make the Event Pipes the primary thing to use for monitoring tools like you shown?
This is the main channel used today. They relied on ETW on Windows and LTTNG on Linux because it was there. And when they started to build the troubleshooting tool set, they relied on what existed at that time, and they realized that they had some drawbacks. Kevin mentioned some of them. I've also mentioned the fact that, for example, for ETW, you get the traces for all application running at the same time. And so they decided to implement that event pipe communication channel plus the protocol on top of that, and build all the tooling, all the CLI tooling that exists today is based on event pipe. So if you want to build something, focus on event pipes. We found out some performance issue in specific cases, but it shouldn't be a problem for most of the applications.
Yeah, I would add that earlier I mentioned the overhead, but I was specifically speaking about the profiler that you can use with the event pipe. And the overhead is from the profiler, not from the event pipe themselves.
Yeah, it's based on the implementation, something close to what you get when you do a full blocking GC, for example, because you have to freeze all the threads to get the call stacks. And that has an impact. But the event pipe itself is enough, I would say.
Okay. Thank you. So I think we have too little time to continue with the questions online on air. So we will be waiting for you in the Zoom discussion zone, and whoever wants to continue discussions with all these performance things with Christophe and Kevin are welcome there. And
Yes.
we will continue with the official closing of the conference in about a minute or two, and then afterwards you can watch that and join the Zoom room with our speakers. And thank you again for joining us on this weekend.
Yeah, thank you very much. We will be waiting for you guys. Bye.
Bye.
Okay, bye.